Yeah, please go ahead.
So, good morning, sorry, good afternoon, students. And today we are going to synthesize a compound by Knoevenagel reaction. And basically, the technique we will use, that is something new, microwave assisted synthesis. Sorry, just a moment. So let's. Okay. We'll prepare this compound using Knoevenagel reaction. But before that, there is one part, microwave assisted synthesis. So this is a comparatively modern technique, microwave assisted synthesis. And in this case, what is the role of microwave? Obviously, the reaction is important. The reaction is there, but in each reaction, there needs some activation energy. But even after that activation energy, the rate of reaction is little bit slow. So it takes some longer time. But if we do that kind of reaction in microwave, microwave actually produce a huge amount of local heating, and that resists the chairing of the compound, rather help to go the reaction upward direction, forward direction. And so we can do any reaction using this microwave assisted process very fast, just within a few minutes. For a reaction that generally take 2-3 days, we can do in microwave within few minutes. And so that is the beauty of these things. But one thing you have to remember, that for microwave assisted synthesis or microwave reaction, you cannot use much organic solvent. Because of this huge amount of local heating, it's always possibility that it can burn and it can burst as well. So we'll avoid using solvent in microwave assisted synthesis as much as possible. And the second thing is that I don't know how many of you have this experience, just boiling water or boiling an egg in a kitchen microwave. So if you do that, you will realize that just within 30 seconds or 1 minute, the entire pot that you are keeping with water inside the microwave, it becomes very hot. And so you need to be careful to take out that pot after that microwave completed its work done. And so that's about this microwave assisted synthesis, how microwave works and everything. And for today's experiment, we will use a kitchen microwave, though there are now microwave reactors are available in market. They are sophisticated instrument and generally used to do the reaction in closed vessel. But for this kind of kitchen microwave, we can easily use to do our reaction in an open beaker. And so for today's reaction, Knoevenagel reaction, we'll use a domestic microwave oven. And so the reagents are para-anisaldehyde. So this is the anisaldehyde, when this is the aldehyde group, and this is the OMe group. So this is para-anisaldehyde. And ethyl cyanoacetate. So this is ethyl acetate, where one group, one hydrogen is replaced by a cyano group. So this is ethyl cyanoacetate. And Shumon will discuss why we choose ethyl cyanoacetate, what is the role of these things. And then we will use ammonium formate. So that is also a salt, but with heating that will break, the salt will break, and ammonia and formic acid will form. So ammonium formate will use, and this is our product from this reaction. So the reaction is very simple and it will just over within minutes. So we'll take 1.32 gram of para-anisaldehyde. This is a liquid. 1.32 gram of para-anisaldehyde. This is liquid. And then 1.13 gram of ethyl cyanoacetate. This is also liquid. So we are taking two liquids in a small beaker, and with that we will add 630 milligram of ammonium formate. So ammonium formate 630 milligram, that is solid, we will add with this thing, and then we will cover the beaker with a watch glass. We will cover the beaker with a watch glass, and we'll keep the beaker inside the microwave oven. And then we'll adjust the microwave power at 300 watt irradiation, and we'll go for 90 seconds. So though for the completion of the reaction we put here 90 seconds, but you can fix it within 1 minute, that means 60 seconds as well. And so just start the microwave. After microwave stop, there will be a beep sound, and then open the microwave door. Initially you will see a lot of fumes inside the microwave, and you will smell the bad smell of ammonia there, and also this aldehyde, also anisaldehyde smell will be also there. And immediately you will see that whatever liquid you have taken in your beaker is completely solidified, a light yellow color, or it's kind of like a lemon color solid appear. And then we'll take out the beaker carefully from the microwave oven using a gloves, because it's really very hot. And so just take it out the beaker, put it on the table and cool it for room temperature, at least wait for 10 minutes. Once it is cool, add some water and scratch the compound with a glass rod. Try to take out all the compound from the side of the beaker, because it will really stuck. As it is from melting condition, it's got to solidified, so it will stuck on the beaker. So with the glass rod, just scratch it and then filter the solid and wash with water, and you can recrystallize the compound from ethyl acetate petroleum ether. So this part is not necessary. Even with the compound that we filtered and washed, we can directly go for the characterization. Okay, and so now any question? Hello? Yes, students, any question? If not, then I am ending this slideshow, and Dr. Sumon will show you the reaction mechanism and other details.
Okay, thank you, Devasita.
Yes.
It's visible, right?
Yes, yes.
All right. So as Professor Haldar already mentioned, the utility of microwave. So just to elaborate a little bit, that microwave, this is basically the rotational energy. The microwave energy is used for the rotational energy of the atoms. It really helps to rotate the different atoms. It's really activate, and it helps to get the perfect conformation, which is the reactive conformation. And also it generates this enormous amount of local heat, which really helps to cross the activation energy and promote the molecules to the transition state, so that you can reach very fast reaction. Okay. And so this is the utility of a microwave. There are, as Professor Haldar mentioned, there are really several microwave reactors now because time is money. This time is money. So industries, they are where they are producing the products in large scale. They really want something to be fast, so then they can cut off the cost of labor or so whatever associated expenditures. So it's a big area of research now, and there are microwave reactors, modern microwave reactors, where you can put down the things in, and then you can do the reaction. But one thing is in microwave the safety feature because it's so vigorous reaction, such a heat generation. If someone is not doing it carefully, it may explode, especially in a larger scale. So that's why the safety features is the most challenging thing in sometimes in microwave. So that's why these modern microwave reactors are really well equipped with really shielding of the vessels. So to put myself used this when I was in abroad. Used this microwave vessels. This is very with hard glass. We have to put inside the microwave reactor, and then there will be a metal chamber where the actual reaction will take place. So these kind of things are there, but these things are really pretty expensive. So you have to spend few lakhs to get one microwave reactor. So this is sometimes it's not really reachable to the common facility. So we decided to show you the concept of microwave, but in a domestic microwave, as Professor Haldar mentioned. But we have to be careful with the reactivity. Anyway, we are doing the reaction in a moderately small scale, and we are heating it really for the very short time of 30 seconds to 1 minute to 1.5 minute maximum, and with a very minimum amount of solvent. Otherwise, normally organic solvents are flammable. If you heat it too much, then it will catch fire. So these things you have to keep in mind. But now comes to the reaction mechanism part. So mechanism wise, it's not really different compared to normal reaction, classical heating reaction or and this microwave reaction is only the activation energy, which is the easy access to the activation energy or easy supply of the activation energy, which is making the reaction faster. Otherwise, reaction mechanism is pretty similar to the normal thing where you just take those things and heat it up or so if required to get the reaction done. Okay, so I will write the standard reaction mechanism here. So what we are taking, so we are basically taking this guy, this aldehyde. We have one methoxy group in the para position, para-anisaldehyde, and CO2 cyanoethyl acetate. Ethyl acetate is when it's a CH3 and then it's ethyl acetate, CH3CO, CO2 and one additional cyano group is there. So it's cyanoethyl acetate. So now the thing is, so most of the organic reaction you will see there is one electrophilic partner and nucleophilic partner. So it's basically nucleophile electrophile reaction. Most of the cases you will see. So you can already understand that this is the with the aldehyde with the electrophilic carbon here. So it should be the electrophilic partner, and this should be the nucleophilic partner. So normally this no, not such nucleophilic center is here. With normally the nitrogen with lone pair also these are there. But we can easily convert it to a good nucleophile. You can see because there is a CH2 here. If you somehow deprotonate this one, then you can form a carbonyl here, right? So that can serve as a good nucleophile. And why this carbonyl formation will be easy? Because you see there one CO2 ET group is there and this cyano group is there. Both are electron withdrawing. So if you can generate a negative charge here, that can be easily stabilized by these electron withdrawing groups. So that's why this deprotonation from this position is pretty easy. Or in other words, this the acidity of this CH2, the hydrogens of this carbon is pretty low. It's more acidic. Basically, pK is low, so it can easily be deprotonated, okay, and can generate the nucleophilic carbonyl. So this is the thing. And what's the reagent we are using here? So is HCO2 NH4 ammonium formate. Okay. So there you can see, as I said, we need to generate this one a carbon ion by deprotonation, but we are not really using any base here. Okay, so we really need some base to deprotonate. So now thing is, this reagent, this ammonium formate, is having a dual role here. Okay, so what's happening when we do the microwave assisted reaction, we just generate local heat. So the first thing happens, this ammonium formate, the salts decompose in two parts. The initial part from where the acid and base from is generated. So it HCO2H, the formic acid, and the ammonia. Okay, so actually this was formed from this formic acid and ammonia. If you mix, it will form ammonium formate. Once you heat it up, it decomposes into the initial acid and base. Sometimes this acid gets further decomposition if it's too much heating to CO2 or H plus. I'm not going into that because that's not important. In our case, actually, this ammonia is the important. Okay? So this ammonia with a lone pair of electron on nitrogen is the magic thing here, and it's actually doing the reaction. Okay, so what's the role of ammonia here? So as I already mentioned, that this reagent is having a dual role. So basically this ammonia is having the dual role. This proton is relatively acidic, so this guy will easily deprotonate the ammonia. Any amine with lone pair of electron is basic, as you know. Ammonia is also have little bit of basicity, which is good enough to deprotonate this guy and form this carbon ion. So our nucleophile is ready. Okay, nucleophile is ready. Now comes to the electrophilic part. So normally aldehydes are okay. It's are moderately good electrophile, but sometimes happen, this especially in this case when there is a methoxy group present in the para position of the ring, as which is capable of donating electron, as you know, plus M effect, mesomeric effect of oxygen, and this guy will go all the way and here, and this will donate here. Because of this mesomeric effect, the electrophilicity of this aldehyde carbon will go down. Okay, so normal, whatever the electrophilicity in normal benzaldehyde, when it's a para-anishaldehyde, it goes down. It's not that reactive. Okay, so it would be good, or we can reach an efficient reaction if you can somehow activate this aldehyde as well. So that's the role of ammonia, the second role of ammonia. So it will activate this aldehyde as well. How? So, so we are using quite some amount of this ammonium formate. So that means we will generate quite good amount of ammonia. Some part will go to deprotonate this one, but there will be still remaining part. So that ammonia, what will happen? So this ammonia will just add here. We'll just add here. Okay, we'll just add here. I'm just showing AR, okay, the whole group. That would be easier and faster. So NH3 plus, and this is minus. Of course, ultimately there is a proton transfer. Here, OH, NH2, and again donate and minus water. It will take one proton from the environment, minus water. Now you see what you generate. This is the guy, NH2, because nitrogen donated its lone pair, it becomes plus. So now it was an aldehyde. Now we generate something which is called iminium ion. So basically this nitrogen just condense with this aldehyde and form this iminium ion. Okay, so now we just compare with the aldehyde. It was a neutral species here, aldehyde, but now it's a cationic species. This cationic species is iminium ion, which is much more reactive compared to the aldehyde. Okay, so it's basically the same carbon here. Okay, previously it was the aldehyde carbon, now it become iminium ion carbon, but the electrophilicity of this carbon is now bit higher compared to aldehyde, so it's pretty more reactive. Okay, so once this get activated by forming this nucleophile was waiting, it will attack here. The follow-up steps are quite simple. Yeah. So AR, I'm just drawing like this, NH2. This is the new bond which is formed. CO2 ET here and cyano here. Okay. The last step is basically again deprotonation. So other ammonias are there around. H3N, it can act as base, deprotonate this guy, and it will kick out this, which will take a proton and then becomes ammonia again. Or you can protonate first, makes NH3 plus, and then also can eliminate as you wish. So that doesn't matter. So you get the double bond, which is our desired compound, CO2 ET and C. Yeah. Okay. So this is the desired product, and it will regenerate the ammonia. So ammonia. So basically, this ammonia, it's which is getting incorporated in the substrate, will ultimately will come out again. So it's kind of a catalysis by ammonia. So it's a catalytic behavior. It is not getting incorporated in the product, in the final product. Before product formation, it's coming out. Okay. Again, this ammonia will go back and react with the other molecules of benzaldehyde and do the same thing again. Okay? Just by doing so, as you can see, the ammonia deprotonates to form the nucleophile. Also, ammonia condense here and generate this iminiamine to activate the electrophile. So that's why this ammonia is having a dual role here, and ultimately this product is formed. Okay. So this is the basically the reaction mechanism. But before closing, just one point I want to mention here. You can see the double bond. This double bond is not a it's tri-substituted double bond with the three different groups around, okay, basically, and one hydrogen. So AR group is the CO2 and CN. Now think about it here. During this elimination, so there are two possibilities. One, when this double bond is forming, this AR and this cyano, it can be in the same side, or the other thing can also form. I'm just drawing it here. We have some space. You can have this also, isn't it? CO2 the other geometrical isomer. So this one where CO2 and air aryl group is in the same side. Okay? But what's happened, this cyano. So take this space and then explain the thing. Just compare the size of the cyano. Cyano with the sp carbon is really linear. Okay, and in other case where the CO2 is here, oxygen, and on top of that ethyl and methyl, it's the CO2 ET group is pretty bigger compared to cyano. Okay, so and of course this aromatic group is bigger than the other part where the hydrogen is. So this is the bigger part and this is the bigger part, the CO2 ET. So it's of course likely that these two bigger part will stay away from each other, and that's the most stable product when aryl and CO2 is away from each other or trans to each other. And that's why this is cyano, and the cyano is on the same side. It will prefer to keep the cyano and aryl in the same side, okay, rather than and these two in the opposite side. That's why this is the major product, and this is the minor product, which is almost not forming. And this major product, where cyano and aryl is in the same side, that will form. So this is the thing, the mechanism. I'll be happy to take any query if you have. Students?
Sir,
Yeah.
in the first step of ammonia acting as a nucleophile,
Yeah.
so this whole like anisole group is like donating. So won't it make more difficult for like the pi star of CO rises, right? So won't it make more difficult for like ammonia to attack it? Like can
Yeah, I
we
mean,
devise a method to like stop the donating effect of MEO, OME, and might make
uh,
it
yeah, you can do something like you can add some Lewis acid sometimes. Sometimes you can donate, add some Lewis acid, which will just chelate with the lone pair of oxygen and then reduce the donation, or some also the Lewis acid will just coordinate with the lone pair here as well, the aldehyde as well. So ultimately the pi star will go down here. Okay. So, ultimately the pi star will go down here. That's the way. Or if you really want to keep the methoxy, or we can just attach some electron withdrawing group here on nitrogen, on oxygen, sorry. Mm. And so these are the different things, these are the substrate engineering you can do. But in this particular case, of course, compared to benzaldehyde, here any kind of nucleophilic attack is difficult. But we have really high amount of ammonia there, So this reagent, because we are regenerating ammonia, we are not really losing ammonia. We have a quite high amount of ammonia with a lone pair of electron. So this is kind of forcing to react with aldehyde group and then form the iminium ion ultimately. Yes.
Okay, so is it that step which requires the heating, like activation, like heating because of microwave and this thing?
Not really. Normally, this carbon-carbon bond formation here, and the carbon-carbon bond formation, this is the rate determining step normally. Yes, because this is a big chunk. Ammonia is tiny, right? So this is quite a big part, and this is also big part, and two big parts are coming closer and then reacting. Normally, this carbon-carbon bond formation should be the rate determining step here, I would say, with highest activation energy.
Thank you.
Any other question? If not, then we'll go
So,
back to you, Josida.
yeah, I have a question to students. So, if any one of you has tried to boil an egg in microwave, kitchen microwave, if not, just try it.
Oh,
Of
no.
course,
It
you will be
explodes.
hard time to clean the microwave later on, but try it and see what is happening. Otherwise, you will not understand many realistic things.
It may burst. Yeah, it will burst. Don't leave it afterwards for your parents to clean. You clean it, please.
Okay, Shmuel.
Yeah, so I will stop sharing. Yeah.
So there are questions in the chat box.
Oh, thank you. Check. Can we use ammonia directly? This is a actually okay. That's a good question. Let me again share. First of all, direct use of ammonia is not that convenient, okay? Because ammonia is a gas, So any gas, using a gas is not that convenient. Although you can use some balloon or so, it's always, if it's much easier or comfortable or convenient if you use as a salt. It's a solid, nothing, you just dump it there. And using a gas, always you need to have extra effort or extra precaution, first of all. And second thing here, although we have shown that ammonia, only ammonia here is as a base and then as a nucleophile and forming the iminium ion, but in several places you see we need proton source as well. For example, here, once you see when it donates, no, this in this first place, no problem, because one of the H can go from here to here, so it becomes OH and this becomes NH2. But after that, you see this donation of this is just donating the lone pair of electron, the nitrogen, not the proton. And here, this guy needs some, I skipped there, but I should mention here that you need some proton also to form the water, no? And then you form the iminium ion. Otherwise, what will happen if you just kick out this OH minus, which is anyway not good leaving group? So it needs some proton assistance so that it goes out. So this in several places, and here also, when here I also skip this protonation because it's quite obvious. Now you guys are chemistry specialized, so this small thing, it's quite obvious things you can I can skip. And, here also when it's deprotonated, no, it's also needs some protonation here so that it goes back so because NH2 minus is also not a good leaving group. You need to make it NH3 plus, then it's a good leaving like this. So it's certain balance of basicity of ammonia. In other side also, some proton source is always continuously required for few of the steps to make it facile. Okay. So that's why if you just only use this ammonia, that the solution will become basic. Hmm. And this extra basic solution is also not good for this particular reaction. You need a certain balance. When required, the ammonia will deprotonate, but when required, this formic acid is actually supplying these H pluses. Okay. So when required, this formic acid will also supply the H plus. So that's why this salt is the best combination. Hmm. The ammonia will deprotonate, formic acid will supply proton like this. Take proton is taken by ammonia, supplying by formic acid. So this subtle balance is very good for this reaction. That's why only ammonia will not be good, and this salt combination is the best. Uh, and yeah, okay. In which step is the microwave required? Normally, this CC, as I mentioned already, carbon-carbon bond formation should be the rate determining step. So that's the most important. And also, initially, to break the salt, the ammonia and formic acid, they are also microwave required. This is the thing. Yeah. Okay. If not, no further question, then we'll go back to Windows.
Yeah, now present that video.
Oh, yeah. Right. We haven't saw the video yet, right? The experiment. Yeah. This is audible, right? Does that? Audible, right?
Yes, audible.
Okay.
Shumon, sound টা increase কর. So increase the sound.
So it's a Knoevenagel reaction.
Is it good enough now?
Yes, it
These
is.
are the chemicals required: anisaldehyd, ethyl cyanoacetate, and ammonium formate. So we have taken 630 milligram of ammonium formate, and now we will mix 1.32 gram para anisaldehyd. So para-anisaldehyd is a liquid, so you have to calculate from the density how much volume of para-anisaldehyd you need. So roughly it is 1.2 ml. So we are placing 1.2 ml of para-anisaldehyd in a beaker 100 ml beaker. So now we will add 1.3 gram ethyl cyanoacetate. So ethyl cyanoacetate is also a liquid. So from the density, we have calculated the amount, and it is roughly 1.2 ml ethyl cyanoacetate. So we are adding the ethyl cyanoacetate with this para-anisaldehyde. And with that, we will add that ammonium formate 630 milligram. So we have added 630 milligram ammonium formate, and now we'll go for the microwave reaction. So in the lab, we have microwave. It's a kitchen type of microwave, but this is okay for microwave reaction with a beaker. So we'll go for 90-second microwave irradiation.
Yeah, so one thing, this Dr. Srikant put a lead here, okay? So better not to keep it open, because we are generating ammonia. So that ammonia is a gas, of course, it will go away so fast. But to stop that, better to keep some lead, although it's not airtight really, but at least the concentration will be higher inside. Yeah.
So our lab microwave was got stuck as it was not used for almost 1 year, and so initially we have some problem with the microwave, but there is nothing to be worried.
Yeah, when nothing works, you restart the thing. Hopefully it will work now. Yeah, I put the timer.
After 90 seconds, we have taken out the beaker from the microwave reactor.
Does you use the same one? It worked out ultimately.
Yes, it worked ultimately, but after long trying, so I removed that videos.
Okay.
Yes, because it was long time Srikant was trying.
Okay,
And
but the
then it's work. Then it's work.
same machine we have used.
Yeah. Same machine. Yeah.
Okay.
Factor from the microwave oven, and now we cool it down, so it is now at room temperature, and we are adding ice to this reaction mixture.
So students can see that we have started with a liquid and now everything got solidified. So just with 90-second microwave reaction, and things comes out, actually it's from all side of the beaker, and that's why we need the lid. Otherwise, it will spread throughout the microwave, and then it will smell very badly.
Mhm. And another thing is, it will be pretty hot inside. Immediately after finishing the reaction, it will be very hot. You have to wait a couple of minutes. Then with a proper gloves, uh, cotton gloves, you can take it out. And then after taking it out, also in the bench, if you keep it in the bench and wait for at least some time so that the temperature goes down. Okay, then only you'll add the ice. Otherwise, if you add with immediately in the hot thing, the glass may break. Okay, so these are the small things we have to keep in mind.
You don't need to weigh the ice, just add 1 or 2 cube of ice and start with the glass rod. So the white solid material we got. So we have started with 2 liquids. One is para-anisaldehyde and ethyl cyanoacetate. The ammonium format was solid, but once we heat ammonium format, that actually uh, breaks into ammonia and formic acid. So, uh, but we got a solid product that signifies that the reaction takes place. And now we'll go for filtration and wash with cold water the product. Yeah.
Is adding a little bit of water. So water is basically the excess salt. You need to remove the excess salt, the ammonium, whatever the leftover. Water will dissolve that.
So you see, just within 90 seconds, the reaction takes place, Knoevenagel reaction. Generally, it takes several hours to complete the reaction, but in microwave reactor, you can do the reaction very fast. So we are now ready for filtration. So we are filtering the compound using aspirator and Bugner funnel. So we have set up the Bugner funnel and we have precipitate of compound in cold water, the yellow color precipitate, that is the compound we got from microwave assisted Knoevenagel reaction. So we will wash this with cold water.
Yeah.
Okay, so students, any question?
Someone asked something. Just stop. Right. Go back there in the chat box. Shiv Kumar. Okay, sorry. I think end part was audible. I hope I increased the volume. And Shiv Kumar said the whole point is doing the best market is to provide a energy required for completion of the reaction. Yeah, just to make it faster. No? So this is local heating, and then this, as I mentioned, the rotation. This rotational energy makes helps the molecule to get the exact conformation, the reactive conformation. So we have learned, no, in the stereochemistry, the conformation. So when we have that this rotational energy of between atoms, it's the exchange between different conformation is much faster. And then or not all the conformations are appropriate for the reaction. There are some reactive conformations, so it's much easy for the molecule to reach that reactive conformations in presence of the microwave. And in many times, this reactive conformation is not the most stable conformation. In N-butane, we have seen, no, different conformations are there with different energy. So some reactive conformations are not necessarily of the lowest energy. Normally, reactive conformations are of high energy. Because of this rotation, the exchange between these different things is much faster. This is one reason. And second is this heating, local heating. And so this is a combined factor. That's why microwave reactions are pretty fast in all the cases. Yeah. Okay, what he asked, if the reactants were solid, the rotational motion would be constrained. It will still be used in microwave. Yeah, that's a yeah. Then it's a problem actually. So sometimes that you need at least some paste kind of thing. Although it's not very safe to use micro solvent in microwave, but people still can reuse, but not in this domestic microwave. That so then you really need these sophisticated machines. So we need to use at least minimum amount of solvent to dissolve the thing. Yeah, that's true. Only with the solid, it may not be that good, but the sophisticated, as I said, no, it's a really thick glass, special glass microwave reactors are there. Microwave basically vials, and you really need to close it, seal the cap. You put everything. It looks like a normal vial, but with special glass where it can resist a lot of pressure. And in the cap, after putting everything, you really need to seal the cap. It's like the cold drinks bottle, the glass bottles, no. So I use personally. So that you have a cap here, and then another instrument. You have to press it so that it really gets sealed. The cap. Okay,
Yes,
and
yes.
after the reaction, with the cap opener, we have to open it. Normally, one-time use. The caps, metal caps are of one-time use. The glass you can use reuse, wash and reuse, but these metal caps are one-time use. Like as I mentioned, that cold drinks caps, glass bottle and metal cap, the same concept. You can put there, and then afterwards you break it and then throw it the cap, yeah, like that. Solvent is required in those cases, minimum amount at least.
Yeah, but if you can do your reaction in water, then it is very easy to do in microwave reactor because water will not catch fire easily.
Yes.
So if the medium is water, solvent is water, you can do the reaction very quickly and safely.
And also sometimes these solids, if it's although at room temperature may be solid, but maybe it's when the melting point is not that high, suppose 60, 70. Then once it's reached that temperature, it melted, and then it becomes liquid. You have nice reaction then, and then in those cases also you don't need to use solvent. But if something is really high boiling, a high melting solid of 200, 300 degree, the melting point, then you need some solvents. Yeah.
So any other question? So if no more question, so let me show you this part. Yes, so once we have our compound, that is the microwave assisted Knoevenagel product. So we have already washed and filtered it, and now we'll go for spectroscopic study. So we can do the FTIR or NMR spectroscopy. So this is the FTIR spectra of the compound we have synthesized. So here the peaks are already mentioned. So you just write this in your notebook. And this is the NMR spectra. So we just draw the compound and assign which peak is responsible for what. So here the integrations are also given. So I don't think it's a problem for you. So do this in your laboratory notebook and submit your laboratory notebook before next day. So that's it about the this reaction. So I will share this in WeLearn shortly. And so if you have any other question, please let me know. Okay, so if no other questions, so let me say you something. So we have 3 more experiments to go. So after that 3 experiments, so you have to do a project. So generally the students do their project in lab, in any of the research lab for 20 days. And so it's your choice. You can choose anything and do the project, which is viable obviously inside the ISA Kolkata, and where the chemicals are available, etc. But for this year, as we do not have any option, so each of you should choose one paper, one reaction, one chemical, whatever it is of your choice, and make your project. So this is online project. So you have to go for the searching through Google and make at least 2 to 3 page presentation, not more than that. So PowerPoint presentation, 2 to 3 pages. The first page should come with the title, abstract, and then the next page is your working formula, what you want to do, and the last page with your result, what you have find. So by that way, you prepare your project, and we'll give your time for that. But to search the project, you can start the searching from now. So we have 3 more experiments to do. So in next 3 weeks, we will complete all the experiment part, and then there will be this project part. So any question? And generally in lab, you do the project in a group, but as this time you are in home, so there is no group, so you have to do project individually. Maximum 3 slides you have to send. Okay, so if there is no more question, so thank you very much, and have a nice lunch.
Yeah, thank you.